Okay, first of all, we need to show that the projection matrix is unique. And in this theorem, we discuss about three properties of the projection matrix. But before getting to this theorem, there is a note which I will use this note later on for some numerical computations. If I have the vector space orthogonal to V, which I represented by V perpendicular, since V is generated by the columns of A, so the dimension of V plus dimension of this orthogonal space is equal to n. We keep this in mind, and then we will use it later on. But another theorem which plays a substantial role in order to get a unique solution for the estimate of responses in a linear model is to show that the projection matrix which obtains this way is unique. Further, we also consider another properties which is symmetric and idempotent. Here, uniqueness means that with respect to the choice of generalized inverse, and unique with respect to specific A. It means that if I consider another P, then those are the same. And the only condition is that the vector space V must be generated by the columns of A. This is the only condition that we need. So V must be a space generated by columns of a matrix. The proof is pretty simple. For the uniqueness, we don't have further thing to say. We will say, okay, since it's a projection matrix, I can write C as P1D according to the previous result, and it is equal to PD. So from this expression, P1 is equal to P. So it is pretty simple. For the symmetry, remember that A prime A, the transpose of A prime, generalized inverse of A prime A is also a generalized inverse of A prime A. So let's start by transposing P. So if I transpose P, sometimes I denote it by PT. So if I transpose the P, then from the fact that A prime AB transpose is equal to B transpose A transpose, I can write it as A prime, A prime A generalized inverse prime, the transpose A prime. And since these are equal to each other, I can and this transpose is the generalized inverse again of A prime A, so I can replace it with the generalized inverse of A prime A, and it follows that it is equal to P, and so it's a symmetric matrix. In order to show that it's an idempotent matrix, we can follow this way, or we can simply show that P2 is equal to A prime A generalized inverse A prime, and then multiply A prime A generalized inverse, and then A prime. From the definition of generalized inverse, I can get it equal to A prime A generalized inverse A prime, which is equal to P. So rather more than this proof, which is also simple, we also have this proof that shows that it's idempotent matrix. And this is actually a definition of idempotent matrix, but here we use it for the projection matrix. This is important because if I have a projection matrix P, then I can also use I minus P, and it is also an idempotent matrix, which after some simple algebra you will get this equality. Here now we want to use the projection matrices. Suppose that I write A as A1, A2, which A1 is orthogonal to A2. So we can simply write the projection matrix, which is defined by this formula as the sum of these two matrices. Further, if the columns of A are mutually orthogonal, it means that ai prime aj is equal to 0 for I not equal to j. So I can write this projection matrix as I can write this matrix vector-wise. Then the A prime A generalized inverse is here. Remember, it's a square matrix. So A prime A is equal to the inverse of A prime A. And since these elements are equal to 0, you have a diagonal matrix. And you know that when you want to invert a diagonal matrix, you only need to invert the elements or entries on the diagonal vector. So here we just invert the diagonals, and then A prime is actually the transpose of this matrix. I must mention that if you have two vectors, let's say b1, b2, and you want to transpose it, then of course a column vector changes to a row vector, and also elements are transposed. So here you see the transpose of A is given by this column vector, but each element is also transposed. So since it's a diagonal matrix, I can simply multiply. Multiply this vector with this vector and then with this one, so we can easily get this formula for that. So for the projection, if I have, this is the important condition, if I have mutually orthogonal, then I can simply write it as a linear, as sum of multiplication of vectors. So in what follows, we try to get a to construct projection matrices on the matrices that have mutually orthogonal columns. If they have mutually orthogonal columns, then I will have a better representation for the projection matrix. So you see, we are playing with projection matrices in order to get nice formulas. Now once again, remember the estimate of the linear mode y hat is equal to py. We discussed it in the previous video, and so I think yes, no, it was in the previous video. I can, based on mutually orthogonal columns of A, if I project, if I construct column space based on these mutually orthogonal vectors in A, then I can simply find the estimate for the response or y by writing py. P obtains P actually is the projection matrix on this space. And replacing this formula above, you can simply write it this way. Once again, I emphasize that these A's are mutually orthogonal vectors. So the estimate is actually sum of projections on the individual mutually orthogonal vectors. So you see the application of projection matrices, and why we are insisting to find better representation for projection matrices in order to get simple formulas. So I can use it in future and write the estimate as the sum of projections on individuals. And therefore the square length of the projection of y on V, which I can also use this notation, is given by y prime py. Once again, py prime py. I can write it as y prime p2y, And since in the previous theorem we showed that the projection matrix is idempotent, so I can write it as y prime py. So the square length which is needed in sum of the squares, whenever you get to the point of sum of the squares of the elements, you need the square length, has a simple formula. And this formula can be used for sum of the squares. Another thing which is important, if we come back again to this result, we see that if we can find mutually orthogonal vectors of A, we will have a very nice representation for y hat, a nice representation, and also for the square length. So we may be asked, how can we find another matrix with orthogonal vectors that I can construct that is space? Here in this theorem we discuss this. So the projection matrix P can be calculated easily by using a convenient basis for V. What I mean by convenient here is a space that is constructed on vectors of a matrix which those vectors are orthogonal to each other. And we will then have an easy representation for that, or better say calculation for that. Here in this theorem we discuss this. Suppose that V is of rank R and it's generated by the columns of A. It is always possible to select a mutually orthogonal basis V, better say the columns of B, in such a way that BS only depends on the first S columns of A. It means if you have A and construct a space on the columns of A, you can always find another B matrix which the columns are orthogonal to each other, which fulfills the condition for this representation. And furthermore, the B2 is only dependent on A1 and A1 and A2. B3 is dependent on A1, A2, A3. B4 is dependent on A1, A2, A3, A4, and so on and so forth. So it's an important theorem, and then you see after this theorem we're gonna go to numerical examples and see how we can use these results. Now let's consider this theorem. Actually, the idea comes from, again, projecting. So we try to project the columns of A on other vectors, and this is possible from the first theorem in the previous video. Suppose the vector A2 from A is given. From the first theorem, that we can write A2 as the sum of B1 plus B2, or better say we express it uniquely. B1 is dependent on A1, so it's a coefficient on A1, and B2 is orthogonal to A1. So actually I'm projecting B1 is better say a projection of A2 onto A1. It means that we are actually projecting A2 on A1, and then we try to project A3 to A1 and 2, A4 to A1, A2, A3, and so on and so forth. So this is the way of construction, but let's see the details clearly. The first two vectors A1, A2 can be replaced by B1 and B2 in the basis without changing V. And furthermore, if B1 is equal to 0, once again I can write B1 as something like CA1, And when b1 is equal to 0, I can conclude that remember the coefficient from the first theorem in the previous video. It is a2 prime a2 divided by a1 prime a1 equal to 0, which means that sorry, it must be a1 here, which means that the numerator is equal to 0, so I can say this guy is equal to 0, and from that we can conclude that a1 is orthogonal to a2, which is not correct, because we assume that these columns are not orthogonal to each other. We want to find a basis with orthogonal columns. So this is not true. It means that b1 cannot be equal to 0, and then we can follow the rest. But in a case that b1 is equal to 0, you can simply assume that b1 is equal to a1, b2 is equal to a2. So we can use the original matrix. But in the original matrix, we assume that the columns are not orthogonal. If they are orthogonal, then we are done. So if we assume that they are not orthogonal, it means that we cannot assume b1 is equal to 0, and then we follow this way. As I said, we can project a3 on b1, so we can use the projection of a3 on b1 and projection of a3 on b2. For this, we can say the vector a3 can be uniquely once again expressed based on the first theorem in the previous video as b plus b3. Here b depends on b1 and b2, and b3 is orthogonal to b1 and b2. So it simply follows that I can write b, as I said, the coefficient of the projection b1, coefficient of the projection b2. So we can write b in this way, and therefore b3, which is orthogonal to b1 and b2, is given by a3 minus b. So this is the construction methodology. We project a2 on a1. We project a3 on a1 and a2, and follow this way. So if we continue this way until we project all elements on each other and replace all ai's with bi's, then we have constructed the orthogonal basis. Remember that when b1 is given by ca1 and b2 is orthogonal to a1, it means that b1 and b2 are orthogonal to each other. So and it also happens for b1, b2, and b3. Then it follows that I can also write, so the proof of the theorem is done. But the interesting and beautiful thing is that I can write the projection matrix based on the elements of B. So and we have now found elements of A1, A2, A3, A4, so on and so forth based on the elements of B. So we can write the projection P as a generalized inverse A prime equal to B prime B generalized inverse B prime. But remember, if the columns are orthogonal, I have a nice representation for that, and then I can represent the projection matrix based on the elements of B. And now we got the convenient representation for the projection matrix. In what follows, I quickly discuss about some examples, and then we go through the sum of squares. Sum of squares of vectors and also the columns. But before that, let's see a very tiny R example. What you need is to define a basis vector, and suppose that I define this matrix as the basis. If if I want to see the basis is given by this formula. Then I can simply write the projection matrix. Although there are some packages that you can compute the projection matrices, but writing the codes for in R for projection matrix is pretty simple. You have the matrix multiplied by the generalized inverse of the matrix transpose itself, and then multiply by the transpose of a matrix. So this is the projection, and then the projection matrix is given by this formula. I quickly pass this code because writing the code in R is pretty simple. And in what follows, I discuss some examples, some numerical examples to see how we can find the projection matrices based on given matrices, and then we go to the sum of the squares. I will stop the video and record another video in order to make it short. Thank you.